Sure, sounds good. Okay, hi everybody. Welcome. Thanks for joining us today at the 15th ECS and Cloud Feedback Symposium on this auspicious day of 22222. Today we have another great set of PhD and postdoc lightning talks for you. So the format will be, we're going to be having 5 lightning talks. Each 5 minutes with 3 minutes for questions at the end. And then we're going to have a short sort of question and answer and general discussion at the end of the session. So if you have any questions or comments about any of the talks, please just type them into the chat. Or if you'd like to ask your question directly, just raise your hand and Nick will unmute you. If you have any ideas for talks in the future, we'll be going back to our normal format in the coming weeks, coming months. So please just reach out to anyone on the executive committee. You can find our contact information and a lot more, including videos of past talks or our mailing list sign up at our website here. So with that, let's start our first talk. Our first talk today is from Brett McKim from the University of Exeter. He's going to be talking about radiator fins and the Longwave clear sky feedback. So Brett, if you want to share your screen.
Okay, can you hear me and see my cursor?
Yes.
Okay, great. All right, yeah, thanks for having me. So this work I'm talking about today is done with Nader Jivanji at GFDL and Jeff Fallis at the University of Exeter. And so my general flavor of my work is that I'm interested in how the atmosphere's radiation and circulation are coupled. And a great example of this is how atmospheric dynamics stabilize the planet against the runaway greenhouse state. And so it was Pierre Humbert who first looked into this, to my knowledge. And so he envisioned this 2-box model of the tropical circulation. We have one box representing region of ascent and one region being regions of subsidence. And so he noted that the deep tropics, the regions of ascent are already close to a runaway greenhouse state. So what stabilizes the tropical climate? And he noted it's the subtropics, the regions of subsidence that stabilize the planet against the runaway greenhouse. And so he referred to this stabilizing role as radiator fins. And furthermore, that these radiator fins manifest as subtropical maxima in the clear sky OLR. But if you actually look at the zonal mean clear sky OLR, these tropical variations that you find aren't that big compared to the global variations. And we know from the forcing feedback framework that it's the feedback that's the more relevant parameter for stability. So what I'm going to investigate is the connection between radiator fins, changes in relative humidity, and the clear sky feedbacks. So I'm going to use a single column model with a moist adiabat. So all I need to do is specify the uniform relative humidity and the surface temperature, and then compute the feedback. And so I can get the long wave clear sky feedback as a function of both relative humidity and surface temperature, indicated in the colors and the contours. And so at low surface temperatures, we find that the feedback revolves around 2 watts per meter squared per Kelvin. And this is a number you find across a number of studies. And it's been talked about before on this symposium series. But in the upper half, in the warmer temperatures representative of the tropics, changes in relative humidity are able to drive changes in the feedback parameter. And so we want to know, why is this occurring only at the higher temperatures? It helps to look at the water vapor window, because Simpson's law says that we should expect very little feedback at frequencies outside the water vapor window. So if you look at the spectrally resolved feedbacks, most of your feedbacks occur within the window. And so if your window closes, then your feedback parameter will decrease. And so we're looking here at the transmission to space, so the proportion of emission that escapes to space from 0 to 1. And at 275 Kelvin, if I vary the relative humidity, the water vapor window stays open, even at 100% humidity. But at 300 Kelvin, continuum absorption activates, so you get this enhanced sensitivity to RH. And so increasing the humidity actually closes the water vapor window. And that's why we're seeing this enhanced humidity dependence in the feedback parameter. And so we argue that these radiator fins manifest as subtropical maxima in the clear sky feedback and not in the clear sky OLR. And the way we're going to show this is by plotting the surface temperature and the zonal mean from reanalysis, and then the free tropospheric relative humidity. And so we're going to use these humidity and temperature pairs and use our phase space as sort of a lookup table. And so if we read off humidity, the feedback, given these two inputs, we get the feedback as a function of latitude, and we get these subtropical maxima, which we're calling the radiator fins. And then we get this minimum in the deep tropics, which we're calling the furnace, and consistent with Pierre Humbert's nomenclature. And so what I hope you take away from this talk is that at low temperatures, the feedback is tethered to this 2 watts per meter squared per Kelvin. But at high temperatures, there's continuum absorption, which leads to this enhanced sensitivity to relative humidity. And that relative humidity variations are able to close the window, and that's what lowers the feedback. And so these radiator fins come from this closing of this enhanced relative humidity dependence. And for more information, you can find my paper at my website, and also there's related, there's longer talks on related work here. So yeah, thanks for listening.
Awesome, thanks, Brett. Does anyone have a question for Brett? I'll ask a quick clarification question, which you might have said this, but what exactly did you mean by relative humidity? Is this like a column average or?
Yeah, so this is, in the column model, we use a vertically uniform relative humidity. But when we use the reanalysis data, we're talking about a vertically averaged relative humidity in the troposphere.
Okay, thanks.
Yeah.
Okay, maybe we should move on to our next speaker, but Brett, please keep an eye on the chat because a lot of times questions pop up there.
Sure, thanks.
Thank you, Brett. Great talk. Our next speaker is Osamu Miyawaki from the University of Chicago. He's going to be discussing energy balance regimes in the modern climate.
All right. Does that look good?
Yes.
Okay, great. All right, thanks for the opportunity to talk about my research here. I want to continue along the same theme of looking at the latitudinal structure of feedbacks as Brett has done, but focus specifically on the lapse rate feedback highlighted here. So an interesting and well-known feature of the lapse rate feedback is that it's negative in the low latitudes and positive in the high latitudes. And the intuition behind this has been out for a long time, going all the way back to Manabe and Weatherall in 1975, who explains that in the low latitudes, you can think of the upper troposphere amplified warming response simply just as a shift to a more warmer, moist adiabat with more latent heat release. And in the high latitudes, as the warming confined to near the surface because the lower troposphere is so stable there. And so this intuition developed a long time ago was nicely illustrated using simple models by Payne et al. In 2015, who showed that you can reproduce these vertical temperature structure of vertical warming responses using the simplest models we have for the low latitude temperature structure, which is assuming radiative convective equilibrium, and the high latitude temperature structure, assuming radiative advective equilibrium. And at the moment, our sort of intuition of where these insights apply are simply that RC applies in the low latitudes and RAE in the high latitudes. And what I wanted to answer and think about is, can we be more specific and systematic about where these assumptions are valid and thus where the insights we gain from RC and RAE are applicable on the real world? So to do this, we first need to quantitatively define RC and RAE. So to do this, let's look at the atmospheric energy budget shown here. I'm going to categorize the fluxes in this energy budget as advective heat fluxes, radiative heat fluxes is net radiative cooling of the atmosphere, and surface turbulent fluxes, which I use as a proxy for convective heating. And so if we divide this equation by radiative cooling, we get this ratio R1 that quantifies the relative importance of advective heating in balancing radiative cooling. So using this metric ratio R1, we can define where exact RCE occurs as where R1 is 0. That's where convective heating exactly balances radiative cooling intuitively. And same thing for RAE. That's where R1 equals this ratio is 1, where advective heating exactly balances radiative cooling. But because exact balances like this are seldom expected to be found in the real world, we're just going to relax this definition to be something that captures the essence of RCE and RAE. That is, we expect RCE ideas to apply as long as convective heating is the predominant stabilizing mechanism. And so that we quantitatively express as R1 less than 0.1, some small number, which we choose as 0.1 here. And advective heating, same logic, that leads to R1 greater than 0.9. And the expectation is as you move toward higher values of R1, that the column should become more and more stably stratified. And so now let's look at R1 here shown in the y-axis as a function of latitude in the x-axis for the reanalysis data. And we find that this intuition that RC is applicable in the low latitudes is true and RA in the high latitudes is true. And we've been able now by quantifying these energy balance regimes, you can put a number to it, specifically based on the threshold values we chose. RC occurs equatorward of 40 degrees and RAE poleward of 70 south and 80 north. So it reveals some of these interesting hemispheric asymmetries in the extent of RE that we didn't know about by just grouping everything together as quote unquote high latitudes. Another thing, as we said, we expect R1 to be associated with the vertical temperature structure stability. So I'm now going to overlay the stability quantified as the lapse rate deviation from moist adiabat shown here in the orange. And the thing here to note is as you go up, it's a more stably stratified column. And we see that R1 also captures this latitudinal structure of the stability of the atmosphere, including this hemispheric asymmetry that I mentioned earlier of the Antarctic being more stable than the Arctic. So this R1 metric is a useful proxy for thinking about the vertical temperature structure to first order. And we also find that it's not only useful for the current climate stability, but also for the vertical structure of the warming response in response to anthropogenic forcing. So this is now showing the CMIP5 projections of the warming binned according to the climatological values of R1 in the historical climate. So the red lines here indicate the warming responses that we get in regions of the CMIP5 model that are in RCE in historical climate, and the blue lines indicate the warming response in regions of RAE in historical climate. And we get this nice partitioning where regions of diagnosed as RCE and the CMIP5 ensemble gets upper troposphere amplified warming and RAE surface amplified warming, consistent with the expectations that we had from the Payne et al. Study. And so what we can take away here is that this metric R1, just looking at it in a historical climate, can give us some insights about what we should expect the vertical structure of the warming to be in the future. And so what might be an implication of this for the ECS community? One hot topic right now is the effect of the pattern of SST warming, where if you have more warming in the West Pacific where the deep convection is occurring, then that will lead to a more negative feedback, and vice versa. In the Eastern Pacific where it's stable, then it will lead to more positive lapse rate feedback. And so when I look at this kind of schematic from Marx in 2016, it resembles to me a lot of the conceptual ideas that's similar to RCE and RAE. So indeed, if we look at R1 now as a function of longitude and latitude, we get this zonal asymmetry where regions of deep convection that we think about in the West Pacific has this is a region of RCE in the modern climate, and the East Pacific is a more RAE-like state. And if you compare this then to the spatial structure of the lapse rate response shown here by Yue Dong in 2020 paper, we get that in the fast response where the warming is concentrated in the West Pacific in a region of RCE, you get a negative lapse rate feedback everywhere consistent with the expectation of RCE. Whereas in the later, slower years, when the warming shifts to the East Pacific, then we get more of this response that you expect from a RAE, where the lapse rate feedback changes sign and becomes positive. So that's just a glimpse at one possible application of these like metric R1 and these ideas in terms of studying the pattern effect in the effect on equilibrium climate sensitivity. And so to summarize, I've introduced the metric R1 to quantify energy balance regimes. I've used that to quantitatively determine the latitudinal extent of RCE and RAE, and we showed that the structure of these energy balance regimes are quantitatively linked to the stability of the atmosphere. And it's also a useful metric to make basic predictions about the vertical structure of the warming and thus the lapse rate feedback in future climates. And for more information, you can find, I direct you to our recently published paper in the Journal of Climate. Thanks.
Awesome, really great talk, thanks. Does anyone have questions for Osamu? Paolo, do you want to unmute and ask your question? Otherwise I can read it out.
Yeah, I saw the question. So he asks, what's the interpretation of values beyond or less than 0 and greater than 1? So if R1 is less than 0, that means that there's MSC flux divergence out of the column, meaning that instead of advective heating, it's an advective cooling. So that's reminiscent of the deep tropics where the rising branch of the Hadley cell exports energy out of the column. So that's where you can think of it as convective heating is now greater than what's required by exact RCE balance. And in that case, I think theoretically we can still expect RCE theories to more or less apply. I think in terms of dynamics, obviously it matters, but for thermodynamics, I think it suffices to group it all together in the same category. And similar idea for RAE, that's just where there's excess energy from advective heating, and that is balanced by surface or sensible heat flux heating the surface from the atmosphere.
Great. Christy, do you want to ask your question?
No, I had the same question as Paula, I just hadn't seen in the chat, so I'm good.
Okay. I'm actually interested in Andy's question, which is how do you calculate R1 from reanalysis data?
Yes, so that's basically we just infer advection here as the residual. So I understand that there's a lot of hesitancy to trust our ability to, the surface turbulent flux. There's a lot of uncertainty. So I think it will be interesting to look at more methodological choices of whether you compute every term and then infer some residual. We haven't done that. We use these terms because if you compute the advection term in the high latitudes, that also leads to the new errors as well. So we chose to use the surface turbulent fluxes from the analysis.
Okay, great, thanks. I think we need to move on, but there's still more questions in the chat. So yeah, please check those out, Sama.
Thanks.
Thank you, Samu. Our next speaker is Huang from McGill University, and she'll be discussing nonlinear coupling between long-wave feedbacks. So Han, when you get a chance, you can share your screen.
Okay. Okay. Hello, everyone. Today, I'd like to share this work with all of you. It's about the nonlinear coupling between long-wave radiated climate feedbacks. And I will mainly use the ENSO case to demonstrate such a nonlinear coupling effect. Oops. Okay, So here, as what we are familiar with, the ENSO is characterized with an increase of sea surface temperature in the central and Asia Pacific region, and also accompanied by the increase of water vapor concentration and air temperature and also cloud cover in this region. And so if we use a CRF, which represents the cloud-rated forcing, to estimate the cloud-rated effect at the TOA, we can get a quite similar pattern as figure C here. But counterintuitively, the CRF at the surface is quite weak. So the question is why the cloud-rated effect at the surface is so weak, even with obvious cloud change in Central Pacific. So this motivates us to investigate the nonlinear coupling effect. And as people are not only concerned about the total radiation change, we are also care about the radiation change due to different components. So there are several common ways people use to decompose the total radiation change into different components. Like here, following the PRP method, if we are concerned about the total radiation change due to temperature, water vapor, and cloud, then it can be expressed in this way. Here, delta R represents the total radiation change, and the R term represents the radiative flux with different atmospheric states. And following a Taylor expansion, we can further decompose the total radiation change into different components, like here, including both linear effect and also nonlinear effects. So actually in the widely used kernel method, those feedbacks are only contains these univariate linear effects. For those nonlinear effects, they're actually attributed to the cloud feedbacks, as the cloud feedbacks are always treated as a residual term in the kernel method. So this will lead to some biases in the quantification of the cloud feedbacks. And here to accurately measure each terms, in this equation, we use a radiative transfer model and the variables at different ENSO phases to simulate the value of each term here, and which can be considered as truth value. And to clarify, here we are concerned about this nonlinear coupling effect from the radiative transfer perspective, rather than why these variables are coupled with each other. And here, this slide shows the nonlinear coupling effect in ENSO case, similar by radiative transfer model. Here, the figure A is a univariate cloud feedback, and compared with the previous CRF result, we can know so cloud feedbacks actually make significant contribution to the increase of surface downward long-wave radiation. And its strength can be as strong as 15 watts per square meters in the Central Pacific. And figure B is a coupling effect between water vapor and cloud. And they show that there indeed exists a significant cloud-water vapor coupling effect, which can amount to 50% or even greater of the univariate cloud feedbacks, for example, in the Central Pacific region. And figure C show that if we artificially attribute such a nonlinear effect to the univariate cloud feedback, then the feedback is largely dampened. So as a nonlinear coupling effect between cloud and water vapor is not that big to be ignored, is there a way for us to estimate it? And here, based on the one-layer atmospheric model, we propose an analytical model to explain and understand it. So here on the left, the schematic shows the radiative properties in the atmosphere, like the temperature T and the absolute depth of water vapor and cloud, tau Q and tau C. And taking the radiative flux at surface as an example, it can be expressed as a product of emissivity and the black body emission in the atmosphere, and also following the definition of the cloud feedback and the coupling between water vapor and cloud, you can actually get such a simplified relationship between these two terms. And the parameters in this model is the delta Q represents the change in total column of water vapor, and the A parameter A actually is something related to absolute depth about water vapor. Then how can we understand this model? First, we can understand it from qualitative perspective. So in this model, as A is always positive, so delta Q determines the enhancing or damping effect of delta RCQ on delta RC. For example, if delta Q is positive, then the coefficient of delta RC in this model is negative, which means that these two terms are of the opposite sign, like in the Central Pacific. And when delta Q is negative, the opposite is true. And moreover, we can understand this model from quantitative perspective. If A is known, then we can use this model to estimate such a nonlinear coupling effect rather than using the RTM to simulate every time. So here we use a linear regression model to determine the A to be 0.2 or 0.1 for surface or TOA respectively. And here the plots show the validation of such a model, and C and D plots are the its biases against the truth value. So the plots here affirm that this model can well reproduce a pattern as well as the strength of such a coupling effect between water vapor and clouds. And so to summarize, here are the main points we find in this work. And if you're interested, you can refer to this paper or contact me directly. Thank you.
Awesome, great talk. Yeah, are there any questions for Han? If not, I'll ask, could you talk a little bit about how this relates to the kind of more traditional ideas about cloud masking, which Brian Soden and others have written about? Is this like a more accurate estimation of the cloud masking effect?
Yes, I think so. I think here we quantify here this word quantify the masking effect between water vapor and cloud. So I think with this model, I think we can better or more accurately quantify the cloud radiative effect.
Okay, thanks. Priyam, do you want to unmute yourself and ask your question?
Sure. Yeah. Yeah. Nice talk. I was just wondering, do these nonlinear feedbacks then cancel temporally and spatially to yield like kernels and other PRP techniques as reasonable for global averages?
I think we can still use kernel to estimate the quantify the radiative feedbacks. But yeah, as a result shown here, it did include some inaccuracy here.
Okay.
I would say I would recommend maybe we can explore other ways, but before that, I think kernel can remain a reasonable method.
Okay. Thank you.
Thank you.
Awesome. Thanks so much. Han, please keep an eye on the chat because I'm sure more questions will pop up.
Okay.
Okay, for our next speaker will be Florian Römer from the University of Hamburg. We'll be talking about spatially resolved feedback parameters.
All right. Can you hear me and see my screen?
Yes.
Okay, great. So hello, everyone. Thanks for the opportunity to give a talk here. I will talk about a method to spectrally resolve the climate feedback parameter using infrared satellite observations. So first of all, why is it interesting? As you know, usually the feedback parameter lambda is analyzed regarding its broadband integral. However, of course, the emission level of OLR, which is shown here, strongly varies spectrally. So for example, in the atmospheric window, between 800 and 1200 inverse centimeters, OLR is mostly sensitive to the lower troposphere and the surface, whereas in the water vapor bands, we actually see effects of the mid and upper troposphere. And so spectrally resolving changes in OLR can give insights into feedback processes happening in different atmospheric layers. And this is actually one of the reasons why the spectral feedback parameter has gained increased interest in the past few years, with a couple of studies spectrally resolving the long-wave component of lambda using models. However, as far as I'm aware, no study has used satellite observations to infer the spectrally resolved lambda. And this is where our study comes in. So how do we go about this? We use a method based on interannual variations. And of course, as the talks last month about the pattern effect again highlighted, short-term feedbacks from short-term variations and long-term warming are of course not the same. However, they are still closely related, and this is why we use this method here. And we use the 13 years of the time series from the infrared atmospheric sounding interferometer to calculate the global mean all-sky spectral OLR for large parts of the infrared. And for the part of the infrared that's not covered by the instrument, we simulate the spectral OLR to also calculate the feedback there. And then we only need the near surface temperature, which we take from the era 5 reanalysis. And then we can calculate the spectrally resolved long wave feedback parameter using a linear regression of monthly deviations from the mean annual cycle. And the resulting spectral feedback looks like this. So the first thing we can check is if we integrate this over the whole long wave spectrum, then we get a value of around -2 watts per square meter per Kelvin, which is roughly consistent with previous studies. Note that this now is the all sky and not the clear sky, but nevertheless, this is roughly consistent. We also see that the strongest feedback, as expected, and as we've seen in the previous talk by Brett McKim, also the strongest feedback also occurs here in the atmospheric window. However, maybe a bit surprisingly, here we also see substantial contributions in the water vapor bands. And this occurs for two main reasons. One of them is, which has been highlighted previously, is that the mean relative humidity profile actually makes a big difference. And so whether you assume vertically uniform relative humidity or more of a C shape, this has an impact here. So this is one part. And the other part is that also the change in the relative humidity matters. And so, of course, with warming generally, we think that relative humidity stays constant with warming. And if we look at the change in relative humidity profile here on the right for our interannual variations, we see that, yes, the changes are small, but especially for the mid and upper troposphere, where the water vapor bands are sensitive to, we see a small but significant decrease in relative humidity of about 0.5% per Kelvin. And this combined effect of the mean relative humidity distribution and the change in the relative humidity profile causes those water vapor bands to actually contribute about 25% to the total feedback. So having a quite substantial contribution here. So with this, I'll wrap up already. So I've demonstrated that it is possible, and we can in fact infer the spectrally resolved long wave component of the long wave. So the spectrally resolved long wave feedback parameter using satellite observations of interannual variability. I've also shown that this resulting spectral feedback is very closely tied to changes in the relative humidity profile and the mean relative humidity. And this study also shows that already quite small changes in relative humidity can have a quite substantial impact on the resulting spectral feedbacks. And this again highlights the importance of getting the relative humidity trends right, also when it comes to long-term warming. And with this, I thank you for your attention, and I'm now open for questions.
Awesome, really great work, and really nice addition to some of the talks you've been having over the past few sessions. Nader has a question.
Hi, Florian. Great talk, and great to see this looked at in observations. It's really happy to see this work, and of course, there's some surprises from the real world as you're highlighting. Just wondering if you made any quantitative estimate of how much the relative humidity trend versus the shape of the mean RH profile contribute? Obviously, you can't do that directly from the observations because you only have two-way fluxes, but maybe you did some rate of transfer calculations to try and tease that apart.
Yeah, so actually, as you mentioned, it's a bit difficult to do that. So we didn't quantify it here in this study. But the study by Kluft et al. Actually looked at least at the effect, the quantitative effect of the relative humidity distribution, and I think they found something like a factor of 2, if I recall correctly. So then the factor of 2 might be attributed to the mean relative humidity distribution, and then the rest, maybe of the difference, then can be attributed to the change in relative humidity. So if I had to guess, I would expect the mean relative humidity maybe having the slightly larger effect, but yeah, we didn't directly quantify this.
Okay, thank you. I mean, a change in relative humidity of -1% per Kelvin seems small to me, but I haven't checked it, so I was wondering if anyone else had. Might be an interesting direction to pursue. Thank you.
Yeah. Chris Holloway asks how confident we are in the reanalysis trends in relative humidity, and how do you think they might relate to long-term, the trends under long-term climate change?
Yeah, sure. I mean, that's the key questions. Because I think one can be somewhat confident that the reanalysis gets the short-term variations right. The question is more whether this is similar to what we can expect under long-term warming. And I don't know the answer to this. I think if someone can quantify this, we would be get a big step ahead, I think.
Okay, we have plenty of time, so Brett has his hand up. Brett, do you want to ask your question?
Sure. So you mentioned that this was using the all-sky OLR, and so I was wondering if maybe some of the contributions to the feedback is due to the changes in the cloud tops. So if you have, proportionally higher anvil temperatures, then they're going to contribute a certain amount of change in the OLR. So, yeah. Yeah,
sure. I expect that to also contribute to this, yeah. But we didn't quantify it either, no.
Okay.
Actually, we tried to also calculate a clear sky feedback, but we had some issues or some difficulties because the clear sky sampling from the satellite, of course, is very different from how clear sky is defined in the model, and so we oversampled the subtropics, for example, and it was quite difficult to get rid of this sampling effect, and so we stuck with the all sky for now.
Thank you.
Okay, thanks, Florian. Please keep an eye on the chat. And I think we're going to move on to our last talk now.
Our final talk is from Yuan-Jen from National Taiwan University, and she'll be talking about the Southern Ocean heat uptake and its role in the time varying feedback.
Hi. Am I in full screen? Okay. Hi everyone. I'm Yuan-Jen Lin. This is a research from myself, Yanting Huang, Zhenliu Fu Kai, and Brian Rose from last year. So we are suggesting that the heat uptake over the Southern Ocean plays a dominant role in changing the long-term projection of the climate feedbacks. So on the left, you're looking at the Gregory plot of the CESM1. So like most of the coupled climate models, it projects a more amplifying net radiative feedback decades after CO2 quadrupling. This change in net radiative feedback is mostly due to the cloud's impact on shortwave radiation, shown as a gray bar here, so far consistent with the previous studies. And what we did here is we consider ocean heat uptake as a forcing to the atmosphere and to the surface, so that we partition some of the climate responses in coupled models into two parts. One is from CO2 quadrupling without any changes in ocean heat uptake. We can simply take the equilibrium responses to CO2 quadrupling in a slab ocean model to represent this term. Note that this term is time invariant, so it does not change the time evolution of the climate feedback. And the other comes from the contribution of the time evolving ocean heat uptake. The way we quantify this term is through running multiple pairs of the simulations, with each being forced by the small patch of surface warming or cooling. As shown here, note that the actual forcing is twice as large, and this overlapping patches will jointly cover all the open ocean. And by analyzing all of the simulations, we got this matrix representing some target responses X, like TOA radial flux, air temperature, etc., to the regional ocean heat uptake. So if we want to quantify how time evolving ocean heat uptake shapes the climate feedback in couple models, we diagnosed the ocean heat uptake from the couple model and applied it with this matrix. And you probably noticed that this is very similar to SSE green function, but a Q-flux version. So what we got from that? Here I'm showing that we do reconstruct the changing climate feedback if you compare these two bars. So that gives us confidence on our quantification. And more importantly, if you decompose this ocean heat uptake term into different latitudinal bands, you will find that ocean heat uptake over the Southern Ocean is the main reason for the changing climate feedback, shown as the orange bars. Okay, so how do we understand this? We can refer to the time evolving surface warming pattern and the corresponding changing stability. Now you are looking at the changes in cloud feedback from the model output on the left, from the global ocean heat uptake reconstruction in the mid column, and the reconstruction that only includes the Southern Ocean heat uptake on the right. All of them agree that there's a strong increase in cloud feedback in Southeastern Pacific. Consistently, when we look at the changes in surface warming pattern and the estimated inversion strengths, we observe the enhanced warming and the decreased stability over the Southeastern Pacific. The mid column here just shows that we can generally reconstruct the spatial pattern of each turn. And the right column here is the interesting part. The ocean heat uptake located in the Southern Ocean not only just locally changes the surface warming in southern extratropics, it has a far-field impact, a remote impact on tropical SSE pattern. To be more specific, it's an enhanced warming in Southeastern Pacific relative to the Western Pacific convective regions. The remote impact from the Southern Ocean on the tropical SSE pattern, followed by a weaker temperature gradient in the upper tropospheres, leading to a decrease in low-level stability and an increase in cloud feedback. So that's a brief summary on how we can quantify the contribution of regional ocean heat uptake on changes in climate feedback, and we point out the dominant role of Southern Ocean. Thanks, and I will take questions.
Some super interesting work. Christy has a question. Christy, you want to unmute yourself?
Yeah, so this is really interesting stuff. Have you, well, how do I phrase this? It's sort of the classical way in which this has been thought of by, like the Brian Rose's and Kyle Armour's original papers on ocean heat uptake and the pattern effect is that the way ocean heat uptake alters feedbacks is still by mediating the surface temperature pattern. So I guess the question is, could you check that by convolving the SST patterns that come out of this model with the radiative Green's function for CAM5 out of Zhou et al. To basically check whether the impact of ocean heat uptake on feedback is just because it impacts SSTs, or maybe there's something else. I don't know what that would be, moisture fluxes or something.
Oh, yeah, I got the point. So so we can see from the figure that it has some implications on SSE pattern, and we can simply guess from the SAT pattern and convolve with the SSE Green's function. So we can explain our result through SSE Green's function, but you're asking if there are some other approaches to affect the climate feedbacks. So that's
Is there something else, or is this just a matter of understanding how ocean heat uptake impacts DSST patterns?
Yeah. Oh, okay. That's an interesting question. I never really quantify that. So thanks for the suggestion. I can quantify that through convolving with the SSE Green's function, right?
Yeah, I think that would be one way of doing it, although the SST Green's function isn't perfect either. So yeah.
Okay.
We can chat more about this offline. There's another, yeah, we can chat more about this offline. I want to leave time for other people to ask questions.
Yeah, does anyone else have questions for Yuan-Jen? If not, maybe I'll keep the meeting going for another 5 minutes in case there's still discussion going on in the chat. And if anyone has any questions for any of our speakers, please, now would be a great time to ask it. Or Gavin, do you want to ask your question? If not, I can ask it. Yuan-Jen, do you think that changes in Southern Ocean heat impact might have similar impacts as anomalous freshwater forcing?
Freshwater forcing in the, from the Antarctica. So there are some ongoing research, as far as I know, are talking about how loss of the Antarctic ice to the tropical SAT pattern. So I'm not sure if that involves the same physical process, but the way I can relate to other processes that in Huang et al. 2017, there's a idealized experiment that they deepen the Southern Ocean mixed-air dust, and they observe a SAT pattern change similar to what I have observed in the tropics. So the way I relate my Q flux Green's function is that the Southern Ocean circulation and the mixed-air days depth in the Southern Ocean could have implication on tropical SAT pattern. And I'm not sure about the Antarctica sea ice loss.
Okay. Jonah, do you want to ask your question?
Yeah, I was curious about, in some of the talks, especially Brett, Osamu's and Hans, there was a lot of looking at the local response of fluxes to surface temperature changes. And some of the work coming out of the sort of SST Green's functions literature looks at the non-local radiative responses and flux responses to surface temperature changes. I was wondering if any of those speakers have looked at the role of non-local feedbacks as it pertains to what they're researching. Just sort of an open question to those folks.
I can give a shot at it. So I think a very direct remote versus local feedback arises in the lapse rate feedback, especially in the RAE framework. I think Nicole's work has shown very nicely that and also together with Ashley Payne's work, that the lapse rate feedback itself depends on the type of forcing in radiative advective equilibrium. So of course, that view has been used to understand high latitude lapse rate feedback, but I think the fact that RE might apply also in this region in the tropics might shed some light into, well, I think it's qualitatively known that there's remote influences, of course, because of the weak temperature gradient in the East Pacific, but maybe that's just one example of understanding local versus remote feedbacks.
Thanks. That makes sense.
Maybe similarly with Brett and Florian's work, like if you have moisture transport and that affects the RH, that could also be a non-local feedback. Yue, do you want to ask Yuan-Jen your question?
Yuan-Dong are asking about how Southern Ocean heat uptake affect the Eastern Pacific SST. So there are some possibilities, and one possible mechanism is through changing the tropical circulations. So if you have this interhemispheric asymmetric heating, then you will trigger the a anomalous tropical circulations in and accompanied with the changing surface wind, and that would have impacts on SST and the stability and cloud feedback. So I think that shortly answered the Yuan-Dong's question, but I know there are some other possibilities that are involved.
Great, Andrew. Oh, go ahead.
No, I'm saying I see Christie's papers. I'll take a look. Thanks.
Andrew, do you want to ask Florian your question?
I can try. Sorry, my internet's not very good. It's not maybe not very well posed, but I was just saying that I was just thinking that, you know, you mentioned IASI has these sampling issues, which made it hard to look at the clear sky feedback on its own. Do you think that would also make it difficult to just compare the spectral feedback with what you might get from models if you took like the spectral output from just RRTM or something? Do you think it would also do you think it generally would make it difficult to just do a comparison between the observations and the models?
So yeah, for the clear sky, I think that might be tricky. For the all sky, I don't think so much, because there the sampling issues don't really apply, because we just take all the data basically, so there's no sampling issue there. So I think that would be a fair comparison. Yeah, so that would be one way to do it. Yeah, of course, we also thought about performing the spectral simulations ourselves, but then we didn't have the high resolution cloud parameters we needed for the all sky simulation, so that was a bit tricky. But yeah, maybe the RTMG bands might be a compromise there. I hope that answers your question.
Yeah, thanks. I hadn't really thought about how you don't really have these sampling issues. Yeah, when you're looking at the all sky. That's a good point.
Okay, so maybe we'll wrap it up there. Thanks so much to all the speakers for just really high level talks, every one of them. And yeah, see everyone next month.
Thanks, everybody.
Great job, everyone.